Let's start now. Formally, I welcome all of you. Good evening, good afternoon, good morning, wherever you are. It's really my great pleasure to welcome my friend Liza to this platform. I think she does not really need introduction in the community of Spintronics, very well-known name. Have done fantastic work on Magnetoionics and domain dynamics, channel-stream-area interaction, and so on. So many things she has done. I was really privileged and happy to be in her habilitation seminar in Paris 3 years ago. And it's very kind of her to accept our invitation on behalf of my organizing team. So co-convener Dr. Prasbhushan Singh, then the other members, Puspendra, Shakti, Azhar, and so on. So I really like to thank you, Liza, for kindly accepting our invitation. I also thank all the participants who are very kind and very supportive in last almost 20 months or so. And this is the 80th seminar. Very nice that Liza is talking the 80th seminar. And I think I can be very brief about her CV, but I will just take the opportunity to introduce a bit. So Liza, as I said, she works on several things. For instance, she has a very interdisciplinary background in physics and chemistry. Between 2003 and 2007, she studied physical chemistry at the National University of Cordoba in Argentina. And from 2008 to 2010, she conducted her doctoral studies at the Max Planck Institute for Solid-State Research, while enrolled in the physics doctoral school at École Polytechnique in Lausanne. During this time, she performed studies on magnetic domain wall dynamics and magnetotransport in devices based on diluted ferromagnetic semiconductors, or known as DMS. She has also designed and realized the concept of light control of magnetic properties in DMS devices by surface functionalization with organic dye molecules. Between 2001 and 2012, she worked as a postdoctoral researcher at Institut Nel in Grenoble. During this postdoctoral work, she worked on electric field control of magnetic anisotropy and domain dynamics in ferromagnetic field effect transistor devices. Since 2013, she is a CNRS researcher at the Center for Nanoscience and Nanotechnology, very famously known as C2N. And her main scientific interests are oriented towards the control of domain wall dynamics in multifunctional nano devices, mostly using Magnetoionics and interface engineering. She has got many awards and so on, but the very important thing is she is also the associate editor in Applied Physics Letter. So with this very brief introduction, I again welcome you, Liza. And before you start your talk, I should say that now we have about 50 people. And I just want to mention that during the lecture, we don't take any questions. So if you have any questions, kindly write that in the chat box or just raise hand. At the end of the lecture, I would like to request Liza to stop sharing. And I would like to request all of you to turn on your camera so that we can take a group photo. And after the photo, right away, we will go to the question and answer session. Okay. So I think with this, I now invite Liza to start her lecture. Looking forward to your lecture. Thank you so much.
Well, thank you so much to you, Subanka, for this amazing, very warm introduction. So, well, as I was saying before, I mean, I congratulate you for this series of seminars, to you and all your group for making this happen. I mean, especially in this last 2 years, so we're very hard for everyone to connect. So then I'm very honored to be the invited speaker for the talk number 80, which is quite a milestone. So thank you very much for this invitation. And I'm thrilled to really be a part of this. So, and I'm looking forward to welcoming you in France whenever that's possible again. So, okay, so today I would like to talk about magnetoionics. So as it goes in the title, so that is using ionic motion to control magnetism. So before I start, I would like to tell you where I'm from. So the Center for Nanoscience and Nanotechnologies is located in the southern part of Paris, so in the outskirts in the south. It's about 1 hour by train to Palaiseau. And we have a very nice building that is all brand new. And I'm in the nanoelectronics department, but we also have a lot of people working, especially on photonics and materials. So, so we are in the campus of the Paris-Saclay University. So then we're very happy to be now in this new building, which is surrounded by such a nice atmosphere of research with, for example, our colleagues in Thales, also doing Spintronics and École Polytechnique, and many industrial actors as well from technology. So it's a really nice place to be, a really stimulating environment. So, well, so let me start by the motivation behind controlling magnetism with an electric field in general. So we know very well that Spintronics is really headed, it's really focused on applications, especially on magnetic memory architectures. So there are a bunch of different types of designs for memory architectures, more developed or less developed. So on the more developed side, of course, there is the spin transfer torque memory. And we also have other prototypes like the spin orbit torque, and also, for example, the racetrack, especially with skyrmions, more like skyrmions related nowadays. And then there is also the VCMA, the voltage control of magnetic anisotropy, is also being proposed as something of very high technological relevance for magnetic memory architecture. So let's list actually what the challenges are and where to try to find where this gating of the magnetism could become important. So of course we have density, so we want to go very small, and we have the limits of fabrication, etc. But one important point, well, in general in society actually, is the reduction of energy consumption. So then that's a very important point for Spintronics these days. So then, for example, we would like to have a system where we can lower the writing currents to store information while keeping long retention times at the same time. So, and then there are other things, there are more particulars for each type of design. For example, the spin orbit torque type of memories, where we need to have field-free switching, improve the charge spin conversion, and lower resistivity, for example. Or in racetracks where we have domain wheels or skyrmions, to be able to really control the pinning, and for example, the skyrmion Hall effect as well, that needs to be controlled in order to use skyrmions on a track for information storage. So what can we do with the electric field? Well, actually, I mean, the electric field provides us with a tool that can be used as a switch. So for example, in terms of energy consumption, the electric field could offer to go from a soft magnetic state, for example, with a very low anisotropy, where we can easily switch the magnetic state with low energy, and switch from that, and once we're done with the writing, then switch back to a hard magnetic state, which we can store safely for a long time, where thermal activation will not be an issue for the information storage. And the same, for example, for domain wheels and skyrmions. So if we want to store information with those magnetic structures, we want to make sure we have them in controlled positions. And then, but at some point, we're going to need to move them, for example, if we need to read the information. So then we want to be able to switch between these two states. Very well pinned for information storage, very easy to move for readout. So this is what the electric field is here to offer. And that is why it is such a promising tool for the design of new spintronic devices for memories. So, so let me tell you how we can control magnetism with a voltage. So you mainly have two options for this. So on the left are the charge effects. So this is the typical field effect transistor structure that you know from all the types of applications. So you have your magnetic film, which is one of the electrodes, an oxide in a top electrode, and you apply a voltage, and this generates a charge accumulation at the surface of, in this case, your magnetic film. So this has a number of advantages, which is it's electronic, so then it's high, it has a high charging speed. So this is basically instantaneous. And it's very much compatible with conventional electronics, with nanofabrication. So this is very much in benefit of applications. On the other hand, it has a few downsides if you like to call them downsides. So it's volatile. So that means that it's a charge accumulation. If you get rid of the applied voltage, then the charges go away, you go back to your initial state. And it is also limited to the top interface. So we're talking about a charge accumulation in a metal. So then this is really concentrated at the top surface. So you also need your magnetic material to be a nanostructure. So then you need it to be as close as possible as a surface, or like the materials that we use for technology in Spintronics, for example, materials with perpendicular anisotropy that is seated at the top interface. So, but then we know that the bottom interface is also very interesting, because if you have a substrate that it's a heavy metal, then you could have DMI actually coming from this interface, and you might want to control that. So this you cannot do with charge effects. On the other hand, you have ionic effects. So the structure of the device could look pretty much the same as the one in the charge effect. So your magnetic film, an oxide, a top electrode. Only that you want to pick an oxide that has high ion mobility. So here, when you apply your voltage, you're actually generating a magnetic field, and you're not so much interested in the charges that you're going to accumulate in your magnetic film, because of course that's going to happen anyway. You're interested in using this electric field to move the ions in the oxide. So the electric field has to be high enough so that the ions can move. And then these ions can move towards or away from your magnetic film. And that is going to create large changes in the magnetic properties of the film. And the good side of this is that it's not volatile. Once the ions are whatever they are, you switch off your voltage and they're going to stay put. So that is an advantage. And of course, that they can penetrate quite a bit into your device. So then the effect can be modulated between the top interface and the bottom interface. You can actually reach down to the bottom interface. And of course, it has downsides as well. So the speed is limited, because here we rely on ionic diffusion. So then we have a fundamental limit, which is the motion of the ions. So we will never be as fast as charge effects. So if you need something to be super fast, then you need charge effects. But on the other hand, ionic effects are non-volatile. And another thing that is still something that the community is working on a lot is the reversibility and the cyclability. Because as we will see later, these ions don't just move around. They strongly interact with the atoms in your magnetic film. So for example, inducing oxidation or reduction. And then this is something that can affect the reversibility of the effect and also the cyclability. So then if you go back and forth 100 times, so you might degrade your material at some point. And this is something that the community is working on a lot these days. So I'm going to focus on the ionic effects today. But before I do that, I want to show you a few works that have been done on charge effects for you to get an idea of what can be done there. So here's charge effect. So this is one of our studies where we could use cobalt iron boron MgO, and we apply a voltage, and then we could see we could go all the way from perpendicular anisotropy to in-plane anisotropy. And what we did with this is to apply a constant perpendicular field, and then just switch the magnetization from in-plane to out-of-plane only by the action of the electric field. So then you can just induce the switching only by the gate voltage. And then there's this very nice work by the people in Grenoble, so in France. So they could see that they could switch on and off skyrmions in platinum cobalt thanks to the gate voltage. And also people have looked at DMI. So I mentioned before that DMI is a lot related to your bottom interface, but of course it's related to the asymmetry between the two interfaces. So then you could still have a shot at changing DMI if you control the top interface. And this is what they did. So they used this charge accumulation to modify DMI. In both these studies, they could see how that affected domain wall dynamics. And then as you can see here, they could also see skyrmions, etc. So there are very nice things that can be done with charge effects as well. So, okay, so let's talk about ionics then. So the ionic effects is obviously what I mean when I talk about magnetoionics. So let me spend a few minutes telling you about what are the different types of devices that you can use for magnetoionics. So you have the solid state devices, which are more or less what I've been sketching so far. So you have a magnetic layer, an oxide, a top electrode. And as I said before, this is more compatible with applications. It has very good perspectives for miniaturization. In general, this is the way to go if you want to build devices. So you want to pick an oxide that has a large ion mobility, and then you just build your device with the usual nanofabrication techniques that we all have. So, and then another thing that I like a lot, and then we use a lot in my lab, is ionic liquid gating. So this is one of our works. So here you can see we have a tantalum, cobalt, and boron layer. We cover it with hafnium oxide. So hafnium oxide has a lot of oxygen mobility, actually is the material of reference for memristors and memristive applications. And on top of that, we put an ionic liquid. So the ionic liquid is actually a molten salt. So it doesn't have a solvent. It's just ions, positive and negative ions only. So then what happens is that when you apply a voltage, these ions would migrate towards the two plates with the opposite charge, and they will accumulate there. So this can generate a very large electric field because actually you apply a voltage and you have the distance between your two plates. But here, the real distance is not the microscopic distance given by the liquid. It's actually the distance between the first layer of ions that is placed on top of the surface. And this can be very, very small. So actually it's estimated to be an effective distance of 2 nanometers. So then if you apply a few voltage over 2 nanometers, you get pretty large electric fields. And then of course, this kind of electric fields can be achieved with solid state devices, but you probably have to work quite a bit to get a nice device in the clean room that can do that. However, ionic liquid is the easiest thing you can imagine. You just put the ionic liquid on top of your surface, you stick a wire into it, and that's your device, and it works. So then it's a very robust and simple way to do electric field and to study the effects of the electric field. Because also you can do it over a very large area. So then if you need a large area for a technique that has a very little signal, for example, this is really the way to go. And then, of course, a lot of people are working really on the electrochemistry side. So this is really what you need to understand actually the chemical changes happening because of magnetoionics. So this is done in an electrochemical cell, which is what you see here. So you have your for example, here your iron film and then contacts, and then you just close all this, and then you have an electrolyte in the cell that can interact with your magnetic layer. So what is important to know is that an electrolyte is not an ionic liquid. So an electrolyte is actually a solution of ions that actively participate in the magnetoionic process. So then you have, for example, iron oxide that is reduced into iron, and that oxide, that oxygen goes back into the electrolytes. Then you can have also ions that get deposited onto your layer because of the changes in the voltage. So this is, the electrolyte is actually very active in the ionic process. This is not the case with the ionic liquid. The ionic liquid is just a tool to generate an electric field. So the ionic liquid does not interact chemically with your layer. So that's a fundamental difference. Okay, so then let's talk a little bit about what kind of ions we're talking about when we talk about magnetoionics. So a lot of what you see on the literature today is oxygen ions. So here you can see, this is the same graph that I've been showing you so far for solid state devices. This has been done with gadolinium oxide. And here they could really nicely observe how the oxygen could be used to modify the magnetic properties. So here what they did in the top layer, you can see that they grew platinum, cobalt, gadolinium oxide, and then they grew also a thin layer of pure metallic gadolinium on top of the cobalt. And then they made it thicker and thicker. And then they just look at the properties of those stacks. And then what they did is like they took this one, for example, and then they said, well, we're going to take this one and then apply voltages to go more towards the gadolinium formation or more towards the gadolinium oxide formation. And this is what you see here. So then they could see actually that the voltage was equivalent to actually growing the layer with less gadolinium or more gadolinium. So this could really show that there was an oxidation front coming from the gadolinium oxide and going closer and closer to the cobalt layer, and that had a really large impact on the magnetic properties. So then from our side, so we looked at the oxidation of cobalt in platinum cobalt films with hafnium oxide, and I will go into detail later on about this. And but here we could see that we could actually see it by X-ray photoelectron spectroscopy that the metallic cobalt would actually transform partially into an oxide. So it would transform into this other peak that you see at higher binding energies that corresponds very well to oxidation. So then this is pretty well established actually that you can really oxidize your magnetic material with this transport of oxygen. And here is one of our recent measurements on cobalt iron boron hafnium oxide on tungsten. And then here you can see once again the oxidation of the iron, the oxidation of the cobalt. But in particular, we can see very well the evolution of the oxygen edge. So then we have a large peak at the beginning of oxygen, which of course there is already oxygen in the system. So we have hafnium oxide. But at some point when we start applying the voltage, we see that the second peak here at, at higher binding energies, so this peak grows with the electric field applied. So then the nice thing about this is that we were able to identify which were the oxygens that were being driven in and out by the electric field. So then we could really see the signature of the mobile oxygen. They had a different electrochemical environment as the oxygen from the hafnium oxide. So. And of course, that's not all. I mean, there are other ions that could be used for magnetoionics. So people have shown already that a mechanism could be seen where the mobile ions are hydrogen ions or protons, basically. So this is the same diagram, the same group that did the gadolinium oxide measurements that I showed you before. And then here they could actually block the oxygen mechanism by adding an extra layer on top of the cobalt, etc. And but then by doing this, they could actually see another mechanism that is driven by the motion of hydrogen. And in particular, they could see that this is related. It's really dependent on the water from the atmosphere. So they could see that they really needed water to be decomposed on the surface of the top electrode, and then that those ions would recombine and then go into the layer as protons. And so then that was really important to acknowledge actually that the water from the atmosphere plays a huge role here, and it does as well in oxygen-driven mechanisms. So you can see very well here that they start from the virgin sample, and then in ambient conditions, they get a large change in the anisotropy. But if they do it in vacuum, there's nothing going on. If they do it in oxygen atmosphere, but dry oxygen, there's nothing going on. And even in a nitrogen environment, but with a little bit of water, then they could see something. So it's fundamental to have water. In our own experience, we could see this, for example, with the tungsten system that I showed you before. So that system requires annealing to get PMA. And then we could see that if you take it straight out of the oven, I mean, there's a reduced magnetoionic response right there after annealing. However, if you leave it sitting on a shelf for 2 weeks, and then you do magnetoionics, and then it's going to be a lot better because actually it had the time to hydrate and then to really incorporate this water from the atmosphere. So then that's really very important for this process. The fact that we need to acknowledge that the water from the atmosphere is also helping a lot for this effect. So So we can also see other types of ions, like nitrogen ions. So this is, once again, this approach more from the electrochemical side. So here they could see that they could usually grow cobalt oxide and then convert it back into cobalt, and then that goes nicely between these two, the ferromagnetic state, and then change it back to a paramagnetic state. So, and with the cobalt nitride, they could do the same. So they could see that the nitrogen could be moved back and forth. And they could also see that the nitrogen transport was more homogeneous. So then it probably has, I mean, it has a front that really goes into the layer. And this is potentially better for the material, because it might damage the material less if you cycle it a lot. So that is a positive aspect. And also the fact that it requires less energy. So then the energy barrier for the motion of nitrogen is lower than for oxygen. So that opens also perspectives for being able to use this materials with lower voltages, for example. Okay, so this is, I mean, these effects are not only limited to ferromagnetic layers. So then we have seen in the literature, for example, this group, they use an ionic liquid to bias synthetic antiferromagnets. So what is important to say about this study is that the same group, before this study, they showed actually that magnetic domain walls can be moved at much larger velocities if the magnetic moment is compensated. So then they grew a similar layer. So then they said, well, if we want to compensate the magnetic moment of the domain wall, then we just have to have something that mirrors basically the magnetic moment in the neighboring layer with an antiferromagnetic coupling. And they did this, and they showed they could go to very, very high velocities by spin torque in this type of systems. So then they took this idea, and then they said, well, let's keep this synthetic antiferromagnet structure, and let's try to apply an electric field to the top one and do magnetoionics on the top layer, so that we can compensate more or less the magnetic moment in the other layer. So, and by doing that, they got huge changes in the domain wall velocity. So here you can see it, it's hundreds of meters per second of difference when they set this state to this state, for example, just by a little pulse of electric field. So then this, I mean, you start to see the interest in applications that I talked about at the beginning. So we're really looking now more at functionalities, and then more and more we get to see actually what we can do with magnetoionics for spintronics. More, I mean, going further than just understanding how the chemistry works, etc. So this is really good for applications. And then, of course, this was seen as well in natural ferrimagnets. So then, in natural ferrimagnets, you also have two lattices that are competing for with the alignment of the magnetic moment. So then they have the two lattices are aligned anti-parallel to each other. So then these are not two layers like this one coupled by a ruthenium layer in between. So these are really two lattices. It's one material, gadolinium cobalt, and they could see that by using magnetoionics, actually with once again with proton motion, they could choose, they could define which one of the lattices was the dominant. So then they could switch between gadolinium dominated and cobalt dominated, as you can see here on the top. And then you can see nicely that the Kerr signal from the cobalt really flips sign as they do this. And then in these systems, if you do a study as a function of temperature of the coercivity, then you typically find in ferrimagnets you have this compensation temperature. So then at some point, the two lattices are perfectly compensated. And then at that point, the coercivity diverges. And they could see that they could move this around with a gate. So then that's also a really nice functionality in ferrimagnets. Okay, so let me now tell you a little bit more of our own work on magnetoionics. So I mentioned already our interest in controlling the properties of the bottom interface of our ferromagnetic layer. with the idea of controlling DMI. So here we went for a stack which has platinum, cobalt, and hafnium oxide. So, so we put the ionic liquid on top, we applied the voltage. So we started with a layer that had in-plane anisotropy, and then after applying the electric field, then it went to a perpendicular state very nicely with very nice domains. And so then we went out to the literature, really to learn a little bit more about this. And then, as I mentioned before, well, this is oxidation of the cobalt interface. So we know very well from previous studies where they did oxidation on purpose that the anisotropy can be in plane when it's under oxidized. And then if you keep oxidizing it, at some point you will get PMA because it will be optimally oxidized. But then if you overdo it, if you keep putting oxygen inside, then you're going to go back in plane. So then this curve is very important for Magnetoionics because this is basically what we do with the oxygen, right? We start at some point here in this curve, and then we just add more oxygen or we come back. So then we knew very well that this meant that we started off with a layer that was under oxidized, and then we just went all the way up here to PMA. So then that we could see that we could drive this transition between in-plane and out-of-plane with the gate, thanks to this controlled oxidation of the interface. So to confirm this, we went and we did some experiments with our collaborators in the US and in Italy. So we did what I showed you before already, this X-ray photoelectron spectroscopy. We could really see the signature of an oxidation of the metallic cobalt. And we could also see the signature here in X-ray absorption spectroscopy. So it's a change in this amplitude of the main peak. But what was interesting as well is that we could see a change in the platinum edge. We could see a shift in these peaks. So then this was an indication that the chemical environment of the platinum could be affected by the ions. So this was an interesting point for us because we wanted to make sure to reach this bottom interface. So the fact that something was going on with the platinum was an indication that the ions were going relatively far. And actually, I mean, I'm not going to show it today, but then Dustin Gilbert, our collaborator from the US, he also performed neutron scattering experiments. And then we could reconstruct the depth profile of our stack and then see that there were even changes in the platinum silicon oxide interface at the very bottom of the stack. So then the ions can indeed go very far. So then this is really what we were looking for, some evidence that the ions could really go and interact at the cobalt platinum interface. So this was the moment to go and see what happens to DMI. So then we perform brilliant light scattering measurements with our colleagues in Paris. So what we do here is basically we measure the non-reciprocity of spin wave propagation. So, and if we back up one step, then let's really define what DMI is in order to understand this. So then, so it's an antisymmetric exchange interaction. So then you have the Heisenberg exchange interaction where all your spins want to be aligned together. However, for the DMI interaction, the spins have an order, but it's non-collinear. So then they don't want to be pointing in the same direction. They just have an arrangement that is, for example, helical. So this is the component that can generate a helical spin structure or skyrmions, for example. So it is an order, but it's not just the usual all spins pointing in the same direction. So, and what is interesting about this is that there is a chirality set by the DMI, by the sign of the DMI. So then that means that winding in the clockwise direction is not the same as winding in the counterclockwise direction. So now, if you look at spin waves, so spin waves are excitations in your spin in your ferromagnetic state. And if you take a photo of your spin wave, I mean, you see, I mean, all the spins rotating in one direction. So now, I mean, it becomes important which direction this is when you have DMI. So then if you have a spin wave propagating in one direction and then winding clockwise or going the other direction, winding anti-clockwise, that's not the same when there's DMI. So basically, if you have these two spin waves going in different directions, so they won't have the same frequency if there is DMI. So then the one that is going with the sign of the DMI is not going to be equivalent to the one going against. So then this is going to generate a shift in the frequency of these two types of spin waves. And this is what we measure to get an idea of the value of the DMI. So then these are the typical spectra that we get. And if we compute this delta frequency, then we could end up with a value of the DMI. So then that's how we obtain DMI. And here we could see that as a function of the time that we apply the electric field, so then here the voltage is fixed, and we just leave the sample longer and longer in the electric field. So that means that we get more and more oxygen inside, basically. We see that the absolute value of the DMI is decreasing. So, we see actually the effects of this in the domain wall dynamics. So we can see that we know that the domain wall dynamics at high fields depend also on D over ms. So then this goes very well with the reduction of DMI. So then the velocities decrease critically as you increase the time of the gate bias. So, oh, sorry. So, oh, I don't see that. Yeah, so then, as I mentioned at some point, so our interpretation for this is that these ions that we know are going very far could be getting in between the cobalt and the platinum, and then making this, inducing a decoupling between the two layers, and also making this interface a little bit more rough. And then this has a detrimental effect on the DMI that we can see here decreasing. But then, of course, I mean, that's not the end of the story. We have seen that in charge effects, if you bias the top interface only, you could still get effects. And we know very well that here we also bias the top interface very much. So then it is really a combined effect between what we do in the top interface and the bottom interface. So a similar result was obtained with tungsten, cobalt, iron, boron, hafnium oxide. So here we can see the DMI decreasing as a function of the gating time for -3 volts. And then, but the difference here is that we started from a PMA state because we had to anneal the system to see PMA. So then we had this PMA state that gradually goes in plane because it gets over-oxidized this time. So this time we start from PMA and we over-oxidize. And this is the study what I showed you already. There we can see very well the evidence for the oxidation of iron, the oxidation of cobalt, and the appearance of this peak of the mobile oxygen. So what is interesting from here is that in this system, especially without a top interface with MgO, which is ideal for PMA, in the as-grown state, we couldn't see anything. There was no PMA, there was no DMI, and no gauging effects. So then here we can see very well that although we are putting oxygen inside, so that oxygen is not the key aspect that is going to give us PMA like in the other systems. And it's known that in systems with a tungsten substrate, the structure of the tungsten cobalt iron boron interface is also very, very important for PMA. So we understood at this point that it doesn't matter how much oxygen we put inside, it will just not we will not see PMA. So that we really had to anneal and then really have this nice crystalline interface between the cobalt iron boron and the tungsten. So this is what we did. We annealed it, and then we could see PMA, we could see DMI, but however, it was non-reversible. So so here, I mean, it's something that we can understand when we think about what we do with the temperature. So actually what we do with annealing is crystallizing the structure. So then in an amorphous film, we have better chances of having ions moving back and forth without much of a problem. However, if we have a polycrystalline structure in grains that are crystallized, I mean, one can think that it's relatively hard to actually put ions through these crystalline areas, and especially to get them out. So the ionic mobility is really affected by this. So, and then at this point we said, like, well, maybe we can find a compromise. Let's try to anneal at a little bit lower temperatures, and let's see if we can find a point in between. So we annealed at 350, so not so well crystallized as 390, and we recovered some partial reversibility. There was PMA, but no DMI. So then I think what we learned from here is that crystalline films are a completely different story for magnetoionics. So amorphous films, the ionic motion can be a lot easier, but in systems that really need crystallization to get the best properties, to get enhanced magnetic properties, then magnetoionics can struggle a little bit working as well as it works in amorphous film. So the last thing I wanted to show you from our results is our measurements on tantalum, cobalt iron boron, hafnium oxide. So here we can see the full spectrum of the oxidation. So then we could go from an under-oxidized state, which was the initial state. Here, once again, we come back to amorphous films. So the initial state has in-plane anisotropy. And then we go little by little to the PMA state, and then we overdo it. Then we just keep adding oxygen, and then it goes back in plane. Then we have this full transition that you can see here. And then we call the first one regime 1. So basically in plane under oxidized to PMA, and then PMA to in plane over oxidized regime 2. So here you can see the plot of the remanence of the loops as a function, once again, of the gating time at a given gate voltage. Well, the first thing you can see is that, of course, if you increase the gate voltage, you can see that things start happening much, much quicker because you're increasing your gate voltage. So that is normal observation. But you can see as well is that we have these two branches, right? We have the first branch, which corresponds to the regime 1. So going from in plane to perpendicular, which is the high remanence state. And then we have a second branch going from PMA back to in plane, right? That is the regime 2. But they really don't look the same in terms of dynamics. So it seems that the first one is a lot faster than the second one. In all cases, the second branch is much slower than the first one. So this is the first indication that something is different between the regime 1 and the regime 2. So although we're just adding oxygen into the system, so we can see very well that it's a little bit more complex than we could have expected. So we went there and measured reversibility. So in regime 1, within the window of gate voltages that we can use in the with the ionic liquid, we couldn't reverse this state. I mean, of course, it doesn't mean that it's completely not reversible. It's just not within the window of voltages that we have. However, the regime 2 was very much reversible. So here you can go from PMA to in plane over oxidized and back and forth. And here we did it for about 10 times. So it really goes back and forth very nicely. So, so for us, we see that we cannot come back in regime 1, but we can go back and forth in regime 2. So then once again, this probably means that the barrier, the energy barrier to go back to the in plane under oxidized, it's much larger than what we can do with the voltages from the ionic liquid. So in any case, it's a very different situation than this. So our interpretation of this is that when we start with an under oxidized state, so we have a surface that has barely any oxygen. So then all the oxygen binding sites are more or less available. So then, and then if we assume that all oxygen binding sites are not equivalent, there are probably some binding sites that are more energy effective than others, more energy favorable than others. Those will probably be occupied first. So then with this premise, then we think that indeed the regime 1 is probably a regime in which all these preferential oxygen binding sites get filled first. And then this leads to PMA. So then once we get to PMA, then we probably start adding more oxygen, and this oxygen needs to go somewhere. And it's probably going to go to secondary binding sites or interstitial sites, or maybe a little bit more into the layer. And then this is the part that we think is reversible. So then, as you can see here, I'm in this dark green dots at the beginning, And then the slide dots coming later, that could be moved back and forth. So what is it? What is a process that we can relate to this? So, so we can think in terms of the iron, because this is an iron-rich film. So we start with metallic iron, and then if we add oxygen, then the iron is going to change into iron 2+. So then it's going to form a first oxide. So then this is a proper chemical reaction. So there is a proper change of oxidation number of the iron. This requires a charge transfer. It's a real chemical or electrochemical transition, if you like. So then, so there have been studies on how the oxygen sticks to an iron surface as a function of how much oxygen you put, of the coverage that you have on the surface. And then they could see that when you barely have anything, then the sticking probability is really high. And then as you start adding more and more, then there's a drastic decrease of the sticking probability, which probably corresponds to this first phase of, you know, as I said before, adding oxygen when there's nothing around. So it just captures the oxygen really, really fast. And so then what happens next? So then you have now iron oxide, and you keep adding oxygen. So then iron has another oxidation number, which is 3+. But then to go from 2+ to 3+, you could go also through mixed oxides, 2+, 3+. But before you even do that, you have to add even more oxygen around the iron 2+ to actually create a chemical environment that would, in the end, create this charge transfer and then really oxidize the iron even more. So here we see that there is a part where this oxygen sticking probability doesn't change a lot. So then this we tend to attribute maybe to a phase which just add more oxygen. The iron is still iron 2, but it's just accumulating oxygen around it. And then in the end, it would just go to iron 3. And then this is actually what they say in this study, that at the very end, they get iron 3. And what I show you up to now, the regime 2 is probably between these two. So then here, you don't really have a change in the oxidation number. It's just iron with a chemical environment with less or more oxygen. So those oxygens are far easier. And I put ox here because we don't really know what this is, if it's an OH, if it's an O2-. So then it's some oxygen species. So these are far easier to remove from the sphere of the iron 2+ than a proper oxide here, like bound to the iron. So then this here, you have to go from 2+ to metallic iron. This takes a lot more energy than actually getting one of these oxygens away from the 2+, while the iron 2+ is still keeps its oxidation number. And what supports even more this assumption is that, which I haven't showed so far, is that actually if we take this state, this is in plane, and then we keep adding oxygen, at some point it will not be reversible anymore. We won't be able to come back to this. So then we think actually that once again, if you overdo this, then you land on an iron 3+, and then you have the same problem as you had here. So it takes a lot more energy to go from here to here. So this is why we, with our limited window of voltages, we cannot see this coming back to this. So, so this is basically what I wanted to show you here. So I think it's very important to take into account what the ions do in the device. So, so as a conclusion, I hope I could show you that we can get large changes in PMA and DMI by using magnetoionics. That it's better to use amorphous materials, because if we need ions to move around in the layer, we don't want them to be stuck or have a hard time going through a crystalline phase. And also that reversibility and cyclability are greatly affected by the chemical reactions between the ferromagnetic metals and the mobile ions. So the ions are not just moving around, they're really modifying the chemical environment a lot wherever they are. So I hope I could convince you that magnetoionics has great potential for Spintronics applications for energy efficiency, but also, I mean, now that we look at these devices and everything that we can do with them, So I think there's a lot new functionalities that we can think of for these devices. For example, we could think of multi-state memories that could be useful, for example, for neuromorphic computing. So I think there's a lot more that we can do with magnetoionics, and we're still in the discovering phase of all the things that we can do. And one of the big take-home messages as well is that magnetoionics means chemistry. So then spintronics is a field that is hardcore physics. However, if we want to use magnetoionics for spintronics, we really have to make peace with the fact that they will be chemistry. So we will have to care about the oxidation numbers and what happens with the different species of ions, where do they go, where do they bind, in which way. And in this case, the key is interdisciplinarity. So then we have to be able to talk to people doing electrochemistry, to chemists that are really working on this chemical reactions, the electrochemical reactions, to be able to understand what's going on. So then we have an interest, and the community is really doing a big effort in bringing together the people working on spintronics, people working on batteries, people working on electrochemistry, and that it is really together that we're going to figure out how to use and how to optimize magnetoionics. So, well, this is my last slide. So I want to thank all my collaborators for their great support for all this work done together. In particular, Rohit Bashat, who is the PhD student who did all the work that I showed you in the last part. And all my collaborators around the world, and of course, the funding from France and from the EU. And thank you very much for your attention.
Yeah, thank you, Lisa, for this excellent talk. I mean, really fantastic way of bringing chemistry and physics together. I'm sure there are a lot of questions. I have a few questions for sure. But in the meantime, I request all of you to kindly switch on your camera. Let's take the photo first, and then we will continue. I should clap for you actually. I forgot to clap for your excellent talk. Yeah, now I see a lot of people. Very good. So, okay. Now you can smile. Cheers. Taking a couple of pictures. Cheers. Professor Basu is there. Very nice to see you. Very good. I see a lot of people have not switched on their camera. Maybe last chance. Okay. Good. All right, thank you. So you can switch off your camera, and Lisa, kindly share your screen again. Okay, so if you have questions, you can either write down in the chat box if you want me to read it for you, just in case your microphone doesn't work or so. If you want to ask the question, you can directly raise hands. Okay, while others ask, maybe I can ask, but could you please share your screen?
Oh yeah, sorry.
Yeah, please. Yeah, thanks. So, could you kindly tell what is the significance of this hafnium oxide? I mean, what is so special about it? Why not NGO, for instance? Because you just need to break the inversion symmetry for having the DMI.
That is, I mean, there is the part about DMI and what we need for spintronics, which is, for example, we know very well that MgO is hard to beat as an oxide for TMR and all the and PMA as well. However, we have to consider that we need to have an oxide that can also show some transport of ions. So hafnium oxide is known very well in the resistive RAM community. So then in the memristor community. So then they use it a lot actually to switch between resistive states by motion of oxygen. So this is very well known. And this is also one of the points that I talked about in the end. So for example, we're kind of discovering, I mean, these oxides where ions move. And actually this is so well known from memristors, for example. So then we really need to talk to them a little bit more. And hafnium oxide is one of the key oxides that is used for for oxygen mobility. So that is why we, well, at least for us, we went with hafnium oxide from the beginning. So other people are using other things that are a little bit more exotic, like gadolinium oxide. But hafnium oxide, we know, is something that is very much out there in technology. So then in principle, if we would have to develop a technology that for applications, hafnium oxide would be a good choice because it's already there in the industry.
Okay, I mean, because the DMI comes from the platinum cobalt interface. So apart from the oxygen mobility, which helps in certain ways, but in terms of, let's say, DMI, do you think if you consider a platinum cobalt NGO and a platinum cobalt hafnium oxide, will there be really any difference? I mean, or there should be no difference?
I think it could, yes, because I mean, we don't only will have a contribution from the oxygen itself in the top layer, but for example, I mean, hafnium itself can contribute to DMI. So then let's say that, for example, we have an interface between the ferromagnetic film and an hafnium oxide layer that is oxygen depleted, for example. There is that maybe has an important contact with hafnium. So that's going to be a significant or non-negligible, at least, contribution to DMI, which could be changed with the oxygen concentration at the interface. So then, as I said before, having an interface in the bottom with a heavy metal atom, of course, is gonna give the dominating component to the DMI. But that doesn't mean that the top one is negligible. And this we can see with the charge-based effect, because with charges, you cannot go to the bottom interface. But people could show that they could still change DMI in this way. So then I think it's really a combination of both.
So is there really study to show the effect of the top layer on the DMI?
Well, I mean, these are the studies that I showed at the beginning for the charge-based effect. So there's ionic motion. It's just charge accumulation. And since it's a metal, they can only accumulate charges in the top interface. This really dies out very quickly into the magnetic film. So in this case, they could see changes in the DMI just by biasing the top interface. So we know that we will do a lot by changing the bottom interface, but the effects on the top one are non-negligible. Yeah.
So, I mean, this you presume, or there has been some quantification by BLS or any other techniques?
Yeah. I mean, these were the studies that I showed at the very beginning. They measured it with different, I think in one case, they were looking at the spacing of the domain pattern to get a value of the DMI. And in other cases, they've done it by BLS, and they really could get a change in the DMI. Yeah.
Nice. Okay. And then I also assume that the voltage control magnetic anisotropy study, the presence of hafnium oxide is also very important, isn't it?
Again, sorry?
For the VCMA, voltage control magnetic anisotropy, that kind of study, the layer, the hafnium oxide, I mean, it has its own significance, or you can also have a replacement for that.
Well, in terms of, I mean, what you want for the control of magnetic anisotropy, so it could be two things. So as I explained at the beginning, there is the charge effects and the ionic effects. If you're going to go with the charge effects, then you don't care so much about the oxide that you have. You just want an oxide where you can apply high electric field, and that's probably all you care about. So it's a high K oxide, a high dielectric constant oxide. So then what you're going to care about is the band structure of your magnetic material, because then you're going to want to look at what is the effect on the magnetic anisotropy of the band filling that you're going to do with your gate voltage. So then that's one effect. So that it doesn't matter so much what kind of oxide you use, as long as you can accumulate a significant amount of charges at the interface. However, if you're going to go with ionics, then you're going to start caring about oxidation at the interface. So because this is really what you do with the ions, you oxidize more or less the interface. And that's how you control anisotropy. And then in that case, you need an oxide that can transport oxygen back and forth. And for example, hafnium oxide, gadolinium oxide, etc. So MgO, for example, is not going to do the trick in this case.
Okay, thank you so much. Let's take some questions from others. Sriram is having a question. Having heterostructures actually breaks inversion symmetry. But what is the role of inversion asymmetry in oxygen migration?
The role of inversion asymmetry in oxygen migration. I'm not sure I get the question right.
I think maybe it's also not very clear to me, but maybe he means like you have the oxide only at one side of the stack, so only that's at the top of the cobalt layer. So he's asking this asymmetry somehow helping the oxygen migration. I mean, if you put another maybe hafnium oxide below platinum, I mean, I'm not sure I'm understanding, but I'm just presuming this. Sriram, if you have your microphone, you may just unmute and ask.
Yeah, that's right. I mean, maybe I can. Oh, okay, there you are. Yeah.
Yes, Sriram, go ahead.
Hello.
Yeah, please go ahead.
Yes, yes, sir. Thank you for the talk, ma'am. Actually, you said that there is an inversion asymmetry over that heterostructure. So actually having the structure itself breaks the symmetry because you are creating the stress over that layer itself. But is there anything that inversion asymmetry does with this oxygen migration?
So this asymmetry does too. So you mean that the asymmetry affects the motion of the ions? Is that your question?
Yes, ma'am.
Okay. Well, that's an interesting question. So I'm not sure the asymmetry itself will affect. I mean, what it could affect is that, I mean, your ions are going to have to move through different mediums as they go through. So then if they want to reach the first interface, they're going to have to move across hafnium oxide, which is completely different from having to move into the cobalt iron boron up to the second bottom interface. So then that's certainly a different process. And then as we could see, for example, in the crystallized films, so you could very well move them in the hafnium oxide up to the top interface. But then if your film is crystallized, then you really have a hard time moving them back and forth towards the second layer. So I think that maybe the difference comes mostly from that the ions have to go through different types of materials to reach the first interface or the second interface. So it might not be as easy to get to the first one and the second one, depending on what you have in between. So actually, one of the studies that I mean, but regarding the asymmetry itself, I don't think that would affect this in any way. I mean, another thing that could affect the process is to have, for example, materials like platinum. They are high that people use them for hydrogen storage, for example. So then we could see that some of these ionic processes could happen with protons. So then you could expect that the ions will be maybe a lot more concentrated in the platinum layer, simply because it's this material that really captures hydrogen, and it's not the same in the top layer. So then this could also give you another asymmetry. But the asymmetry itself having an effect on the ionics, I see it only from the point of view of the ions traveling through different types of materials. I cannot hear you anymore. Let me see. There is a problem. I'm going to stop sharing. Sorry, I stopped sharing. I couldn't hear you anymore. So I'm going to share again. No, Subanka, I still cannot hear you. I think your mic is off.
Okay. Yes, I'm sorry.
Okay, no worries.
Thank you. I think Sriram has another question, but maybe Sriram, you can write directly. It's again related to the oxygen migration. Is there anybody else who wants to ask a question before we can close? Please raise hand. Okay, if not the case, then I think I request Liza to stop sharing. I like to share my screen to present a small token of appreciation to you. Okay. I hope you see my screen now.
Ah, yes.
Well, we don't meet in person, but this is something that is a digital plaque. We like to present you from the team for your excellent talk, and really appreciate your time and efforts to coming to the platform. So W2S seminar webinar series on Spintronics, National Institute of Science, Education and Research, NISA, Bhubaneswar, India. Takes pleasure in presenting this plaque to Professor Liza Herrera Diez from CNRS and University Paris-Saclay in France, in recognition and appreciation for being a valuable speaker to give a lecture on Magnetoionics using ionic motion to control magnetism. So thank you so much, Liza. Excellent.
Thank you very much. I mean, thank you for the dedication of preparing this this nice plate for me. And
by email. So
thank you very much.
So let's keep in touch. And I like to thank all the participants for your excellent participation. And see you next week. I think we have Professor Singh Pai from Taiwan. And next week, same time, 8 p.m. So until that, please stay healthy, stay happy, and see you next time. Thank you, Liza, again.
All right. Thank you very much to all of you.
Yes, thank you. Good night. Have a nice day. Bye.